All right, hello, welcome to this week of our Math 2413 weekly review. This week we're going to be covering derivatives of logarithmic functions and related rates. So first thing I want to get started off with is with our logarithmic functions. So first thing we're going to do is we are actually going to go ahead and introduce a couple new rules. So we're going to have a new rule. And this rule is going to state that if we take the derivative of a log function with any base b of just plain x, then that is going to give us the result of 1 over x times the natural log of b. We can actually go ahead and take this a step further, because if we wanted to go ahead and use our natural log function, well, that's going to go ahead and be our natural log function is just essentially log base e. So if we plugged this in, we'd still get 1 over x, but then that natural log of e is going to cancel out to just 1. So therefore, it's just going to be 1 over x. So now let's go ahead and try to do something a little more complex. So now we understand what our logarithmic function is. Let's try to move a little bit forward. Let's go ahead and try incorporating this with chain rule. So we want to go ahead and take the derivative of the natural log of sine x squared plus 2. All right, so now let's think about what we're going to do first. We know we're going to use our log rule, but we also need to think about what we're going to do in terms of chain rule. So we can see that our outermost function is going to be that natural log. So we can go ahead and let this say that we have y equals natural log of u. We can then move in a little further and say that u is going to be sine of some function b. And then if we move into that innermost function, we can now say that v equals x squared plus 2. So now let's think about our chain rule and get it set up. So we have this time we have 3 different functions. So we want to ultimately find dy over dx. And to do that, we're going to end up having our derivative of y with respect to u times our derivative of u with respect to b times our derivative of b with respect to x. All right, so now let's go ahead and look and see what we're going to have with each of our rules. Okay, so we know that dy over du of natural log of u is going to just be 1 over u, base of our natural log rule. Now let's move in a little further. You can see that du over dv of sine of v is going to just be cosine of v. And move in one more step of where we have dv over dx is going to equal, or of x squared plus 2 is equal to just 2x. So now let's go ahead and plug everything back in. So now we're going to have our 1 over u, which we already so we're going to have 1 over u. And we already said that u is a function of v, which is a function of x. So we're essentially plugging in that v back into our that x into v and v into u. So we're going to be getting v left with sine of x squared plus 2. Now we're going to have our dv, our du over dv. So now we already said that's cosine of v, and we already know that v is equal x squared plus 2. And then lastly, we're going to have our dv dx, which is just 2x. Therefore, our final answer is going to be 2x cosine of x squared plus 2 over sine of x squared plus 2. This brings us to something a little interesting. So let's go ahead and take a look back at our original setup. Inside of our log function, we have this full setup, sine of x squared plus 2, which we can see is once again comes back into the denominator right here. We can also take a look at that inner function as well. If we take the derivative of sine of x squared plus 2, that's just a simple chain rule to where we get 2x cosine of x squared plus 2, which is once again what we have right here in the numerator. Well, this pattern is going to apply to pretty much any logarithmic chain rule. So we can actually go ahead and go one step further and say that anytime we're using chain rule with the log function, we can say that the derivative of our natural log of u is going to be equal to 1 over u times du over dx. Or if we just want to put this in terms of where everything is in terms of x, we can also say d over dx times the natural log of g of x is going to be equal to g prime of x over g of x. So now let's move on to another problem that's we can go ahead and try to use our new chain rule. This time, we're going to find the derivative of the natural log of 3x squared plus 2 over x to the 4th plus 2x cubed. Alright, so now let's think about what we have. We can go ahead and say we have a natural log of a g of x. So we know that our g of x is going to be equal to 3x squared plus 2 over x to the 4th plus 2x cubed. Now we need to go ahead and find our g prime of x. So we have a function on top and a function on the bottom, so therefore we can apply quotient rule to find our g prime of x. So now let's apply our quotient rule. Our quotient rule, of course, is going to be our denominator, x, which is x to the 4th, plus 2x cubed times the derivative of our numerator, which is going to be, so the derivative of 3x squared plus 2 is going to be just 6x, minus our numerator, times the derivative of our denominator. So derivative of x to the 4th is going to be 4x cubed plus the derivative of 2x cubed, which is going to be 6x squared, all over denominator squared. All right, so now let's go ahead and clean this up a little bit. So we can go ahead and combine some like terms. So on the top, if we distribute out that 6x to our denominator, we're going to get 6x to the 5th plus 12x to the 4th. All right, now we're going to have our 3x squared plus 2 times 4x cubed plus 6x squared. 3x squared times 4x cubed is going to be 12x to the 5th, but we have a negative sign, so I need to remember to distribute that. 3x squared plus 6x, 3x squared plus 6x squared is going to be 18x to the 4th. Once again, a negative, so to distribute. Then we have 2 times 4x cubed, so 8x cubed. Distribute the negative. And lastly, 12x squared. Once again, distribute the negative. Now, before I go ahead and put this all over our initial function, let's see if we can go ahead and get rid of anything. So we have a couple terms of x to the 5th. And then we also have a couple terms of x to the 4th. So now we can rewrite this as saying that we have, so now we can rewrite this saying we have negative 6 x to the 5th minus 6x to the 4th minus 8x cubed minus 12x squared all over x to the 4th plus 2x cubed squared. It's going to be our g of x. All right, so now let's go ahead and move forward and put this now let's go ahead and move forward and actually put this together into our logarithmic rule. So once again, we had a g of x. Yeah, so once again, our problem was natural log of 3x squared plus 2 over x to the 4th plus 2x cubed. And we already established that our g of x is 3x squared plus 2 over x to the 4th plus 2x cubed. And then our g prime of x was negative 6x to the 5th minus 6x to the 4th minus 8x cubed minus 12x squared over x to the 4th plus 2x cubed squared. All right, so now let's plug this in. So we know that our log rule is going to give us, so the natural log of g of x, the derivative of that, is going to equal g prime of x over g of x. All right, so we have our g prime of x, so negative 6x to the 5th minus 6x to the 4th minus 8x cubed minus 12x squared all over x to the 4th plus 2x cubed squared. Now, just to kind of clean things up a little bit, let's go ahead and just say we're going to have 1 over g of x. So let's say we're going to have multiply this times 1 over 3x squared plus 2 over x to the 4th plus 2x cubed. So if we look at this right here, we can actually see that in our denominator, so if we split our denominator up into its own function, into its own fraction, we would have an x to the 4th plus 2x cubed squared in the numerator, and an x to the 4th plus 2x cubed in the denominator. So we can go ahead and actually just cancel these out. So now we would be left with having negative 6x to the fifth minus 6x to the fourth minus 8x cubed minus 12x squared over x to the fourth plus 2x cubed times 3x squared plus 2. If we want to go ahead and stop here, we can, but we can also still go ahead and simplify this a little more if we want to. So let's go ahead and just pull out. You can go and pull out a negative 2x squared, which will give us 3x to the fifth plus 3x cubed plus 3x squared plus 4x plus 6. And in the denominator, we can pull out an x cubed. So we're left with x plus 2 times 3x squared plus 2. We can cancel out those x squared, so we can go ahead and say our simplified answer is going to be negative 2 times 3x cubed plus 3x squared plus 4x plus 6 all over x times x plus 2 times 3x squared plus 2. And that is going to be the derivative of that initial logarithmic function. So now we see how this works. So now we see how we can go ahead and use our logarithmic functions in terms of chain. So let's go ahead and try one more example before we move on to logarithmic differentiation. So now this time let's try a tangent line problem. This time we want to find the tangent line of f of x equals the natural log of x times log base 2 of x at x equals 2. So let's go ahead and get started with this. We have natural log and a log base 2. Now, even though those are technically different bases, they're both log functions, and we can actually just go ahead and apply product rule to this. So first thing let's do is let's go ahead, actually before we even derive, let's go ahead and find what our y value is. Let's go ahead and find our f of 2 before we move on. So our f of 2 is going to be, we're going to get natural log of 2 times log base 2 of 2. Now let's go ahead and see if we can actually simplify this a little bit. If we think about logarithmic functions, they're essentially the inverse of exponentials. So what we can do, so for example, if we have a function that, let's say, so now let's think about what we have. So essentially what we can do is we can actually cancel these out by turning these into exponentials to see if we can solve. So we know we can raise both, so let's go ahead and say we have natural log of 2 and we want to see if it equals some number a. And we want to see if log base 2 of 2 equals some number b. What we can do is we can actually raise a natural log function and actually put that in the exponent of a regular e to the x function. But we have to apply this to both sides. Similarly, if we have a log base 2, we can also apply this to both sides. So now in this case, we have 2 equals e to the a. We can't really solve for a, so we're better off just leaving that natural log of 2 there. But this time, we're getting 2 equals 2 to the b. Well, we know 2 to the 1 equals 2, so therefore we can let b equal 1. And therefore we can let this log base 2 of 2 cancel out to 1. So we can just say f of 2 is natural log of 2. So now let's move on to finding our f prime and our f prime of 2. F prime of x is going to be using our product rule. So if we go ahead and say we're going to take our logarithmic function, our natural log function, times the derivative of our log base 2 function. And as we said earlier, log base, if we take the derivative of that log base 2, we're going to be left with just getting 1 over x natural log of 2. Now, if we leave our log base 2 alone and take the derivative of our natural log, we're going to get 1 over x. So now let's go ahead and move on to finding our slope, which is going to be our prime of 2. So as we said, we know that we have that natural log of 2, which we know can't be turned into anything, times 1 over 2 natural log of 2, plus our log base 2 of 2 times 1 over 2. So let's actually look at this and see if we can simplify even further. We can see that we have a natural log of 2 here, as well as one in the denominator right next to it. And then we also said earlier that this log base 2 of 2 is going to cancel out to 1. So therefore, we can actually say this equals 1/2 plus 1/2 equals 1. So now that we know our slope and our point, we can just plug this into our point slope and say that we have y minus our y naught, which we already said was going to be natural log of 2, equals m, which we already said was 1, times x minus our x naught, which is 2. So we can go ahead and bring this out and say that we have y equals, so we have 1 times x is just x, 1 times negative 2 is a minus 2, and we go ahead and bring over our natural log of 2, and that is our final tangent line. So the reason I wanted to go over this problem is it's going to introduce a concept that we're going to use in logarithmic differentiation. So what we've been doing is derivative of a log function. Logarithmic differentiation, though, is a slightly different process. So when we do our logarithmic let's go ahead and think about what logarithmic differentiation actually is. So sometimes we'll be stuck in a situation where the way a function is currently written, we cannot derive it. And usually this is going to happen a lot if we have a function. This is usually going to happen a lot if we have a function such as, let's say we have y equals u to the v, where u equals g of x and v equals h of x. We don't really have a way to derive a function raised to another function. But we can still manipulate, however, we can actually go ahead and manipulate our functions in order to get them in a form to where we can derive it. So what we actually do a lot, especially when we have a situation such as this, a function raised to another function, is we use logarithmic differentiation. So now let's go ahead and let's just go ahead and say what the process is first. So when we do logarithmic differentiation, what we can do is we can manipulate our function using the powers of logs in order to get them into a way we can actually derive them. So what we're going to do for step 1 is we are going to take the natural log of both sides of y equals f of x and use log rules to simplify. Step 2. We are going to use implicit differentiation to derive both sides with respect to x. And lastly, for step 3, we can solve for our y prime. So this all seems kind of like, now we have this, but it seems kind of theoretical. So now let's actually go ahead and see what this looks like in practice. So let's say we want to derive the function (3x cubed plus 4 to 1 over x). Well, we don't really have a way we can do that using our normal natural log rules. So what we can do is we can actually go ahead and rewrite this as saying that we have a function y equals 3x cubed plus 4 all to the 1 over x. Now we can go ahead and proceed with step 1 and take the natural log of both sides. So now we're going to have the natural log of y equals the natural log of 3x cubed plus 4 all to the 1 over x. So what we can do now is we can actually go ahead and using our exponential log rule, we can actually, since this is inside a log function, we can actually pull this exponent out and move it in front of the log. So where we can now say that we have natural log of y equals 1 over x times the natural log of 3x cubed plus 4. Now we are in a form where we can derive. So now that's going to go ahead and bring us to step 2. Step 2, once again, was just doing implicit differentiation with respect to x. So if we take natural log of y, we're going to get y prime over y is equal. On this side, we have product rule, so we can say that we have 1 over x times the derivative with the chain rule function is going to be the original function in the denominator, so 3x cubed plus 4 times the derivative on the numerator. So derivative of 3x cubed plus 4 is 9x squared. Plus, if we have the derivative of 1 over x is going to be negative 1 over x squared times our initial function, so natural log of 3x cubed plus 4. All right, so now we're in a spot where we can go ahead and solve for our y prime, which is going to be our last step. So what we can do is we can actually multiply both sides times y to where we can get y prime equals y, which is, so it's going to be y. But we also know, once again, that y equals 3x cubed plus 4 to the 1 over x. So we can actually just go ahead and substitute that in now. Times what we already had over here in purple. So we have 1 over x times 9x squared over 3x plus 4, 3x cubed plus 4. Let's go ahead and just cancel out this x right here, where we get 9x over 3x cubed plus 4 minus natural log of 3x cubed plus 4 all over x squared. And that is going to be our final derivative. So it's a lot of algebra and a little bit of some manipulation, but ultimately we can actually go ahead and use our logarithmic rules to go ahead and be able to actually derive these functions. So now let's go ahead and move on to related rates. So now let's think about what related rates actually are. So the way that I personally would define related rates is related rates are problems where we have two or more different but related aspects chain with respect to another variable using usually time. So this seems kind of vague just in general because there's a lot of different related rates problems we can do. We have some that usually we have a lot of geometrical ones where they can usually involve volume or surface area changing. We also have a lot of distance problems as well, such as like one person moves this direction, another person moves this direction. How far away are they changing? Like how much is the distance between them changing? A lot of things like that. So first, let's go over how we can go ahead and strategize for related rates. So related rates, you initially kind of end up getting some information, but now let's think about what to actually do with that. So now here's what I would say is a strategy. the first thing I would do is draw a picture if possible. Of course, there may be some where you may not be able to draw a diagram or a picture, but usually you can at least get some sort of idea you're working with. Two, analyze the problem for given and needed information. So, for example, what we can do, so for example, just kind of read through the problem and see, okay, they gave us this, this, and this. What are we looking for, though? 3, convert info to symbols relating to the problem. So typically when I say this is try to get some sort of mathematical symbol or some sort of label, that way we know exactly what is what. And that way we can actually go ahead and start figuring out, okay, this is what we have in terms of math, and then that can go ahead and actually help us get to the next step, which is find an equation to relate all values. I'm going to put a little star by all because sometimes they will give us information that we don't actually need. But usually this kind of helps us get an idea of, okay, what equation can we use that to where we have only one thing to solve for, essentially. Five, derive both sides using implicit differentiation, usually with respect to t. I don't think I've personally ever come across a problem where you didn't derive it with respect to time. Like you're going to do that like 99, if not 100% of the time. But you may occasionally have some weird problems where it's related to something else, but usually it's just going to be with respect to time. And then 6, plug in info and solve for whatever you're looking for. So now let's go ahead and try applying this to a few actual problems. All right. So now let's have our first example. We have a perfectly shaped ice cube that is melting at a rate of 0.25 centimeters cubed per minute. How fast are the sides or are the length of these sides changing when they are 1 centimeter each. All right, so now let's go ahead and first thing that we can do is we can go ahead and go to step 1, which is going to be drawing our picture. So we know that we have a perfectly shaped ice cube. So just a little simple cube. There we go. And we know it is melting. So we know it's going to, so we know that it is shrinking. So there we go. So now let's go ahead and think about and analyze our problem to figure out what we have for our info. So they say we know that it is melting at 0.25 centimeters cubed a minute. And we also know we're trying, they're going to, the sides are going to be 1 centimeter. And we're also looking for how fast is the length of the sides changing. So now let's go ahead and start converting this into our symbols. So we have 0.25 centimeters cubed a minute. Since we have that minute, we know that this rate is related to time. And since we know that our unit is centimeters cubed, that cubed indicates that it's volume. So therefore, we can say that our dV over dt is 0.25 centimeters per minute. But there's one other thing to take into account, is that if it's melting, our volume is getting smaller, so we actually need to go ahead and put a negative out in front since our change is negative. Now let's go ahead and look and see what else they give us. We know they are looking for, we know they said how fast are the length of the sides changing. So we know that we're wanting to find the change in the sides. So ds over dt is going to be our question mark. And then lastly, they tell us that we're looking for it when our sides are equal to 1 centimeter. All right, so now we're done with step 3. So step 4 is find an equation to relate all values. So we have something related to volume and we have something related to size. So therefore, we can say, and we also know that the volume of a cube is equal to just the side length squared. Cubed, I mean. So now we can go ahead and actually derive both sides with implicit differentiation. So now we can say dV over dt is equal to 3s squared ds over dt. So now we're at step 6, which is just plug in our info and see what we get. We already know that dV over dt is negative 0.25. That 3 is just a constant. We already know, they already told us that our sides are 1, so 1 squared, and we don't know our ds dt. So at this point, we can just divide by 3, which will give us a final answer of ds over dt is equal to negative 0.25. Well, we know that's all equal to 1/4 over 3. So we can actually simplify this down to negative 1 over 12 centimeters per minute. It's also important to make sure you pay attention to your label, because if you don't have, your unit, because if you don't have your unit right, even if you have the right value, that can kind of indicate, oh, you were solving for something else, you know? So like even if you got, like if you wrote centimeters squared per minute, even if that's the right value for the sides, that unit indicates that you were solving for area. So you always have to make sure you check your units, make sure everything is consistent and what it's supposed to be at. All right, so now let's try another one. This time, actually, I'm going to go ahead and type instead because these are getting long. This time we have a cylindrical water tank is being filled at a rate of 2 meters cubed per hour. How fast is the water level rising when the tank is filled to a height of 3 meters and has a radius of 2 meters. All right, so now let's go ahead and think about what we have and what we're looking for. So first thing we can do is draw our picture. So it says cylindrical water tank, so therefore we can just draw a cylinder. All right. So now let's go ahead and read through our problem, see what information they give us. They said it is being filled at a rate of 2 meters cubed per hour. They also want to know how fast is the water level rising. They said height of 3 meters and radius of 2. All right, we can even go ahead and add some of this. We know this is 2. We know that height right there is 3. And we know that water is coming in at a rate of 2 meters cubed an hour. And we're wanting to know how fast is the water level going up. All right, so now let's look and see what we have. That meters cubed, once again, can indicate that a change in volume. So we can say that our dV over dt is equal to 2 meters cubed an hour. They already told us that our H is 3, our R is 2. They're wanting to know change in water level. Water level is going to relate to height, so it's going to be, so that's going to be dH over dt is what we're looking for. Now the last thing is that we have to pay attention to is our R. So do we have a dr dt? Well, dr dt. If we think about this, this is a tank. And whenever you fill a tank, it's going to go ahead and just everything's going to spread out as much as it can before the water level rises. That being said, if we already have that radius is not going to change because that's just a solid tank. It can't spread out any further, and it can't compress any further just because it's liquid. Therefore, our dr dt we can say is 0. Okay, and let's not forget our units, meters per hour. All right, so now let's go ahead and get going. Now let's see if we can find an equation to relate everything. So they give us a volume, so let's think about what our volume equation is. So the volume of a sphere is equal to pi r squared h. Well, we can figure out something in terms of volume. We know our r and h, and we know our dr, and then the only thing we have to solve is dh. So now let's go ahead and derive both sides with respect to time. It's where we can get dv over dt equals, so we have an r and an h, so we're going to have to use our product rule. So we can say that we have 2 pi r h dr over dt plus pi r squared dh over dt. Now it's just a matter of plugging things in. dv over dt we already said was 2. Then we have 2 pi, we know r is 2, we know h is 3, and then we know dr dt is 0. Plus pi, once again r is 2 squared, and we're looking for dh over dt. So now it just becomes a simple problem of just solving for dh over dt. So since we have a 0 multiplied times everything in this first section, we can just go ahead and just cross it out. So now we just have 2 equals 4 pi dh over dt. So we can go ahead and move that 4 pi. So we can just say that dh over dt is going to be 1 over 2 pi meters per hour. All right, so now we've done a couple ones like that. Now it's involving us kind of filling, like volume changing or something like that. Let's try something a little different. This time we have 2 bikers leave from the same spot. First one travels north at 8 meters per second. The other leaves 5 seconds after the first and travels east at 5 meters per second. At what rate is the distance between them changing 20 seconds after the second biker leaves. All right, so now let's go ahead and go back to our first, of course, our first part of our strategy, which is draw a picture. So we know they leave from the same spot. So let's call this their leaving spot. We know that the first biker leaves and travels north. So he's going to go up. And we also know that the other one leaves and goes east. So he's going to go this way. We know there's going to be a right angle right there. And then they're wanting the distance. So distance is going to be this part right here. So we're going to have our x, our y, and our d. All right, so now let's go through our problem and look and see what information we can pull. So we know the first one travels north at 8 meters per second. We know that the first one has a 5-second head start. And we also know the second one travels east at 5 meters per second. They're looking for what rate is the distance changing. And then they also tell us 20 seconds after the second leaves. All right, so this actually gives us a lot of information we can work with. So first thing they tell us is that since that first biker is traveling north, that one's going to be our y. So we can actually say that our dy over dt, the rate at which the first one is moving, is 8 meters per second. We also know that the rate of the second one is changing is going to be 5 meters per second. All right, and then let's see, we know that they're looking for the change in distance. So dd over dt is going to be our question mark. And the last thing they explicitly give us is they say the time, and I'm going to say time sub x is because that's whenever the second biker leaves is 20. Is 20 seconds, and therefore, since the first one had a 5-second head start, t sub y is 25 seconds. All right, now let's look and see what we can do using this information. We can actually go ahead and figure out what to do with having an x and y and a d. Because we can go ahead and use our Pythagorean theorem. We can go ahead and say x squared plus y squared equals d squared. We can go ahead and start to derive this. We can say that 2x dx over dt plus 2y dy over dt equals 2d dd over dt. But we have a problem. We don't know x, y, and d yet. But we can actually still go ahead and solve for it, because if we have a rate in our time, we can use that to figure out the distance. So we can go ahead and use the formula rate times time equals distance. So if we know that the rate for the second driver, if we know that dx over dt is 5 meters per second, and we know that the time he's traveling is 20 seconds, then we know he traveled 100 meters. So therefore, we can say x equals 100 meters. Similarly, we can go ahead and do the same thing with our y. We know that he is traveling 8 meters per second, and we know he's been riding for 25 seconds. Therefore, he traveled 200 meters in that time. So now we have our x and y, but we still don't know our d. Well, we can still go ahead and work with that. Since we can actually plug this into our original Pythagorean theorem. If we know that our x is 100, and we know that our y is going to be 200, then then we can square both of those and add them to give us our d squared. So we can get 10,000 plus 40,000 equals d squared. 50,000 equals d squared, square root, square root. Well, we can go ahead and pull out 100, and then we can go ahead and divide this by 10,000 and pull that out to where we can say that we have square root of 100 squared times 5 is equal to 100 square root of 5, and that's going to be our d. So therefore, we know that our d, our distance, is 100 square root of 5. Now we finally have all of our information that we can use to plug into our initial problem. So just to clean things up, we have a 2, a 2, and a 2. So let's go ahead and just erase those just to kind of make life easier. So we get x dx over dt plus y dy over dt equals d dd over dt. Now we can just plug things in. We get 100 times 5 plus we can get 200 times 8 equals 100 square root of 5 dd over dt. We can now say we have 500, 1600 equals 2100, which equals 100 square root of 5 dd over dt. Divide by 100 square root of 5. Then we can say that dd over dt equals 21 over square root of 5 meters per second. So yeah, you'll usually run into a few distance ones as well. So normally, once again, there's usually going to be a Pythagorean theorem setup very similar to this. So now the last type of related rates problem I want to go over is going to be the shadow problem. So shadow problems tend to come up a lot, and in my opinion, they're kind of the most complicated to visualize, but once you can kind of get the hang of trying to go ahead and solve for them, they're not awful. So for this example, a light is mounted on a wall 5 meters above the ground. A 2-meter tall person is moving toward the wall at 0.5 meters per second with a starting point 10 meters away from the wall. After 4 seconds, how fast is the tip of the shadow moving towards the person? All right, so now we have this one, and this time this setup is going to be a little interesting. So first off, let's go ahead and we can just go ahead and start with our diagram. So we know that we're going to have a 5 foot, so we know we're going to have a 5 foot tall or a lamp 5 meters to the ground. And if we think about the way light shines and creates a shadow, if we have a 2 meter tall person right here, that light is going to come down like this, and then this is going to be, the shadow behind them. So now let's think about what we have. We know that we have a 5 foot tall wall, or 5 foot tall light, or 5 meters, 2 meter tall person, and then we have a shadow behind it. So now let's look and see all the information we have. We know that we're going to let this be y and this be x. We know a sun is 10 meters. We know that the y of the light is 5 and the y of the person is 2. We also know that x is changing if he's moving closer to the wall, then we can say that that distance is decreasing, so we can say it's negative 0.5 meters per second. Yeah, let's see, we have 5 meters, we have our 2 meters, we have our 0.5, we have our 10, we know t equals 4, and then lastly what they're looking for is let's call it ds dt, but we may have to play with these variable names a little bit. All right, so this setup is a little different. Now let's think about how we can relate these. So let's go ahead and call, let's go ahead and call this little distance of the shadow right here x sub s. And then now let's actually go ahead and change that right here to where we have x sub s right here. Now let's also call this distance right here between the person and the wall, let's call this x sub p. And we know this is that speed is in relation to the person. So now that we have this, let's see if we can figure out how to relate everything together. Because ultimately the thing we're looking for is dx sub s over dt. So one thing we can see right here is that we actually have a similar right triangle. since we have this big one right here with the height of 5 and the length of being that total x, and we also have this smaller one with the height of 2 and the length being, and that width being x sub s. So we can actually go ahead and create a proportion. What we do is we can say that 2 over 5, which are the two heights, can be related if we know that the little width or the x value of that smaller one is x sub s. We can plug that in. And then we also know, once again using the properties of the similar triangle, that that one's going to be xp plus xs. Now what we can do is we can cross multiply times both sides to where we can get 2xp plus 2xs equals 5xs. You can move a little further and just move over that xs to where we can get 2xp equals 3xs. Now we're in a format where even if we have a lot of extra information, we can still move forward. So we have an xp and an xs. We don't know exactly what xp and xs are right now, but we do have the information to solve it. But what we can do is we can go ahead and derive this, since ultimately we're looking for how are they changing, not where exactly they are right now. So we can say that 2 dxp over dt equals 3 dxs over dt. We do have an xp and we do have an xs. Or, well, we don't have an xs, but we are looking for xs. So what we can do is we can actually go ahead and start plugging stuff in like we normally would. We can say that 2 dxp over dt is negative 0.5 is equal to 3 times dxs over dt. We can just divide by 3 on both sides, so we get, so over here we get 2 times negative 1/2 over 3. This cancels out to negative 1, so therefore we can say that dxs over dt is changing at negative 1/3 meters per second. Let me move that over here, clean it up. Now, since it indicates it's moving towards the person, we can even just say 1/3. But you have to just double check to make sure, if you change your sign, just make sure whether or not it actually indicates where you can or not. If it says, for example, if this said moving towards the person, you couldn't change that. But if it said moving in general, then you would have to keep that sign. But if you're in doubt, leave the sign. But there are instances where you may be able to. You just have to make sure you read very, very carefully. Well, that is all I have this afternoon. So good luck on any future assignments and have a wonderful day.